Hi there, and thank you for your interest in the TimeHat. Depending on which configuration you purchased, you'll either get everything seen in this picture or everything seen in this picture. The difference being a pre-configured microSD card. This video is going to be sort of a setup and walkthrough for the configuration, including the microSD card. And in this case, I'm going to be attaching it to a Raspberry Pi. This is a Raspberry Pi 3 Model B+. So the purpose of the TimeHat is to provide the Raspberry Pi with a very accurate and stable real-time clock, as well as a GPS disciplined clock. So as you can see, the TimeHat module itself is very simple. It just has two components. The first is a battery-backed real-time clock module. This is a Maxim DS3231 SN model, and this provides excellent short-term stability and also excellent long-term stability. This is a temperature compensated oscillator with a plus or minus 2 ppm per year, which is really incredible. And then for the long-term stability, we have a GPS module. This one in particular is the uBlox Max M8Q. And this is a GPS receiver that supports both GPS and GLONASS satellites. I believe it can be reconfigured for Galileo and Baidu as well, but by default it comes configured for GPS and GLONASS, and it provides really good worldwide coverage. And so in addition to providing typical GPS information like latitude, longitude, altitude, speed, it also provides the 1 pulse per second signal that is used to really set the precision and accuracy for the rest of the system. So what you want to do to get started for setup is first to attach the hat to the Raspberry Pi. So when I ship them, I thread these M3 screws into the standoffs first. You'll want to remove all 4 of those so that it can fit snugly onto the Raspberry Pi. And we'll go ahead and attach it here. The main thing to be sure of is that, that this is properly aligned. It's easy to accidentally step it up a pin or two in either direction, and you want to make sure it's squarely attached with all pins going into the header there. And then it will sit down flush and square. Any Raspberry Pi with the 40-pin GPIO is supported, and most other ARM single-board computers with this header should be supported as well, though I only have experience with the Odroid C2. Next, what you're going to want to do is actually screw in the standoffs. One thing that's important to note is that on some Raspberry Pis, these holes are a little bit too small. So you can see on this one, they go in just fine. In others, they might be a little bit tight. So just keep that in mind. The Raspberry Pi boards have a lot of clearance here, so you definitely won't damage anything if the threads of the screw bite into the circuit board just a bit. So once your hat is attached, you'll take your SD card here. It can be a little bit tricky to pick up. And pop it down securely into the socket. You'll thread in or screw down your GPS antenna. In fact, in this case, I've already got one mounted in the windowsill here. Let me pull its coaxial cable forwards. And bear with me one moment. And get that threaded in nice and snug. The puck antenna itself should really be somewhere where it has decent sky view. So pretty much anywhere, you know, near near or in a windowsill works really well. You know, if you can put it outside or up in an attic, that works really well too. Once the GPS antenna is connected, next you're going to want to connect an Ethernet cable. Let me feed mine over here. Plug in our Ethernet cable. And then finally, we'll plug in our source of power. I'm using I think this is a 5.2 volt, 2.5 amp power supply. And I have, in my image that I supply, I clock down the CPU a little bit for increased stability. So the power draw on this isn't incredibly high. I find it pulls anywhere between 2 to 3 watts is pretty typical. So you could use a power supply with a little bit less current, but I recommend at least 2 amps. So as soon as it boots, this green heartbeat LED will start to flash in this pattern. The red LED is just the power LED. It's a little bit hard to see, but underneath the RTC hat, there's also a red LED letting you know that the RTC module has power. The GPS module doesn't have a power LED on it, but it does have a PPS LED. So as soon as it gets a satellite lock, that LED will start to flash once per second. So now that this is booted up, we can connect to it from our computer software and take a look at what we've got. Alright, it's about a minute later, and you can now see that the green LED on the GPS module is flashing. So this means that we have a valid lock, and we are getting that PPS time pulse out of the module. Alright, so now that your TimeHat system is booted up and running, the next thing we need to know is its IP address so that we can connect to it and make sure that everything is working okay, and also so that we can start to use it as a network time server. So finding its IP address can be achieved in a couple different ways. The easiest and most direct way to do it is to simply plug it into a monitor or a television using the HDMI port. And right there on the boot up screen, it'll tell you what the LAN IP address is. That can be a little bit cumbersome sometimes, and it's really not necessary. If you have access to your router's administration configuration page, it should list all the clients on your network, and this should be listed under the host name of TimeHat. Additionally, depending on how your router's DHCP and DNS servers are configured, you may be able to connect to it by connecting directly to the TimeHat host name. In my case, I know the IP address of my machine, so I can immediately start to work with it. And the first thing that I like to do is to run this utility called NTP check by Galleon Systems. It's a very simple tool. You plug in the IP address or host name of an NTP server, and it tells you its status. And so in my case, I know that the IP address of my box is 172.16.1.11, and if I click test, then it instantly pulls in all this information. And all this looks good. We know that it has a GPS reference, and we've got a valid timestamp from it. That's really all I'm looking for. I don't really look at the precision or any of this stuff. I just want to make sure that it's using the GPS as a reference, that it's a Stratum 1 primary reference, and that the timestamp looks correct. So that's the first check, is just to make sure this works as an NTP server. And frankly, at this point, you could stop. The next thing I like to do is use a web browser, and by typing in that same IP address, we can pull up the GPSD included PHP script that shows us the status of our GPS. So this shows us the satellites in view and gives us a nice graphic of it. It also tells us what our dilution of precision is, error estimates, as well as our location information. So this is a useful thing to check on periodically. Every time you load or refresh this page, it will pull in fresh data from the GPS daemon on the server. So just useful tool to really get a quick look at what your sky view looks like. So now that we've checked out that and we've confirmed that it's working as a time server, we can SSH into the machine itself and take a look at some other things. So in this case, I've just got the Windows command prompt open. You could also do this from the macOS terminal or from an application like PuTTY or TerraTerm. So we're going to run SSH, and then the username is just TimeHat at the IP address, which again, in my case, is 172.16.1.11. And this is configured as a DHCP client, so it'll automatically pull an IP address as soon as it's connected to your network and booted up. And the password is also TimeHat, all lowercase. And then once we're in, since my image is based on DietPi, it'll pull in some additional information. So the current version of DietPi, the date and time, the temperature that the system is running at. It'll show you your IP address again. And then there are some other commands built into DietPi that are useful. One is the CPU command. So that needs to be run as a super user, so I'm using sudo, and it'll ask for your password again, which again is TimeHat. And this will tell you, again, it'll tell you your current temperature, some information about your CPU. This is an ARM v7L or 1, not sure exactly. And then the frequency it's running at. So I've got my image configured to be locked to 800 megahertz. So that way it consumes a little bit less energy, it doesn't get quite as warm, and it's also more stable than if either it was at its highest frequency or if it was fluctuating between different speeds. This just keeps a more stable clock. Another utility we can run is called GPSmon. This gives us a real-time stream of information coming out of the GPS daemon. Again, this is just like hitting the page in your web browser, just an easy way to get a quick look at what's going on. Finally, there are a couple different tools that we can run specifically for the time server aspect. So the particular piece of time server software that I've chosen to go with here is Crony, and there's a client utility called CronyC, and if you run that, you'll get a prompt. You could also put commands directly into the user prompt. I'll show you that in a moment, but I'm in the CronyC prompt here, and I can type tracking, and this will give me some general information about the status of my time server. So it tells me we are primarily working off of a GPS reference, so we're Stratum 1. This is the time, the UTC time as of my running that tracking command, and then a few other statistics. We can also run the sources command, and this will tell me all of the sources that Crony is configured to use. So in this case, we have our local GPS, and then 3 different NIST time servers. You can configure these to be whatever you want. I'll show you how to do that in a moment here. And if you're not sure what each of these columns means, you can rerun sources with a -v, and that will give you a breakout to tell you, okay, this pound symbol here means it's a local clock, the asterisk here means it's the current best, and then for these remote servers, the caret means that it's a server, it's a remote server, and the dash means that it is not combined, so it's not in use. Then it tells you their stratum and how often they've been registered recently, and then their adjusted offset, measured offset, and estimated error. So in this case, the estimated error for our GPS is 409 nanoseconds. A similar command to sources is source stats. I can go ahead and run that with the -v as well. And this will give us some statistics about those individual servers. So again, we have how many sample points in the measurement, residual runs, the estimated frequency error, error and frequency offset, etc. So just a couple of very useful commands to run. Generally speaking, over time, the system is going to get more accurate as this runs, as it can sort of adjust itself in. So this has only been running, now for a couple of minutes, but already it's pretty accurate. All right, so we can exit out of this, and like I said, you can also run those commands directly. So again, if we run cronc and then tracking, we can pull in the tracking data. Or if we run cronc sources-v, we can pull in the information about the different time sources. So that's a very useful utility. If you want to edit those included servers and change them to be something else, for example, if you have more than one time server in your house, like I do, you could enter them all in here so you could compare them against each other. That's done by editing the cronny configuration file. So that needs to be done as root. So again, you'll use sudo, and then nano is the text editor that I like to use, and then the file is in etc, and it's just called cronny.conf. And then these 3 servers are what you can adjust for your remote servers. I'm not sure if cronny has a limit. I think the most I've ever run is about 15 or so you can plug in extras. These other lines here, this is the most important one. This is the one that creates the socket that GPSD connects to in order to send the GPS time sync information into cronny. RTC sync tells cronny to use the real-time clock. This tells us to log an event if there was a time adjustment made. I believe that 0.5 is regards to 0.5 seconds, but I'd have to double check. This is the directory that it logs to. By default, I have logging turned off so as not to be too aggressive to the SD card, but you could turn this back on if you wanted to capture some of this information. And then really the only other one here that matters is allow all, which means just by default this allows all clients on your local network to connect to it. I highly recommend reading up on the cronny documentation to learn more. It's a very powerful piece of software. Finally, one more utility that's useful to be aware of is just the hardware clock command. That also needs to be run as root. And what this does, the command I just ran there just pulls the time that's in the hardware clock. So this just tells me that it's set properly. That's expected. Cronny is going to automatically set the hardware clock, I think, every 11 minutes. So it's going to periodically adjust this and keep this accurate. The battery-backed hardware clock in the TimeHat is especially useful for a couple different cases. So one, if you temporarily lose satellite coverage, the clock that's built into the Raspberry Pi, the onboard oscillator, is not very stable. And so using the software real-time clock alone, your clock's going to drift a lot. Granted, as soon as your GPS coverage comes back on, it'll readjust and everything will be okay. But while your GPS signal's out, it's going to drift and that could cause issues. So by using a real-time clock, you won't have that problem. Additionally, since it is battery-backed, if you need to unplug your system for any reason, like if it needs to be moved, it'll keep its time. So you plug it in, boot it right back up. It's just going to immediately have the correct local time. So that makes a lot of things go smoother. But that's it for now as far as the software configuration. Again, like I said, this is based off of DietPi. They have a very comprehensive suite of documentation on their website, which is just dietpi.com. And then under, where do they have documentation? I think it's under Getting Started. And then here. Yeah, the /docs. So they have a bunch of documentation about how to configure it further and do all sorts of things with it. I don't recommend using a network time server for anything other than a network time server in order to maintain stability. But there are a few other little things you could add if you wanted to. And DietPi is really just based on Debian, which is the same operating system that Raspbian is based off of. It's very lightweight, it's very fast. And my configuration boots up in about 20 seconds. It uses very little RAM, it's very efficient, so it's a good tool. So yeah, thanks everyone for your interest in this, and feel free to send me an email or leave me a comment below if you've got any questions or you think there's anything I can improve on. I'd love to hear from you. So thank you.